My name is Max Donath, and I'd like to welcome you to our seminar series, Advanced Transportation Technology Seminar. And before I introduce our speaker for today, I am going to give the mic over to Hannah, and Hannah will get through some housekeeping issues related to the course and the seminar.
Thanks, Max. Hi, everyone. So we do have as usual, we have an audience watching online as well as in the room. So for everyone in the room, I would ask that you hold your questions until the end. And when you do ask a question, please hold the microphone up fairly close to your face so those online can hear. Everyone in the room also please sign in on our sign-in sheet at the table over there before you go so we know who's attended. For those of you online, we ask that you sign in via the chat on the upper right-hand side of your screen and tell us how many people are watching from your location. The USDOT does require that we report our number of viewers, so having an accurate count would be very helpful. For students in the class, if you have handed in a write-up, please see me afterwards and I will hand that back to you. And please hold, I think I already said this, but hold your questions until the end. Thank you.
It gives me great pleasure to introduce our speaker, Professor Linda Boyle. She is a professor and chair of the Mechanical and Industrial Engineering Department at the University of Washington. She has an interesting background. I should point out that she first grew up in Brooklyn, went and got her undergraduate degree at the University of Buffalo, then went to work at Boeing for a number of years, and while she was out at Boeing decided to pursue a master's degree and then a PhD degree at the University of Washington. Following that, she then spent 2 years being a researcher at the Volpe Center in Cambridge, Massachusetts, and then subsequently became a faculty member at the University of Iowa. So she was at the University of Iowa for a number of years before she ended up joining the University of Washington in 2009, if I remember correctly. Yeah. So she's been at the University of Washington since 2009. She won the NSF Career Award in 2006. She's an associate editor of Accident Analysis and Prevention. She is the chair of the TRB Committee on Statistical Methods and has been nationally recognized in many areas associated with human factors and human-centered design. And so without further ado, Linda Boyle.
Thank you very much. And thank you, everyone, for coming and listening to my talk. I hope that you'll find it interesting. I do a lot of research in human factors, and so I'm going to go over some of the research that I've done over the past 5 to 6 years, which has been primarily on looking at modeling the effects of drivers' adaptive behavior on system safety. So to begin with, when I look at safety, I look at it from the road user perspective. And my goal actually is to get the road user to their destination without any injury or undue harm. And to do that, I basically look at designing systems, services, and policies that can help enhance the road user's overall health and well-being. And I do that by looking at using various tools and models to identify factors that can help reduce the risk and enhance the safety of everyone that uses the transportation network. Primarily focusing on the behavior or the driver themselves, what my goal is to make sure that we design systems that can actually take into account what's going on with the user. And basically, when we have these new systems that are coming on the road, and I talked a little bit about that yesterday, we're looking at systems that actually have the capability now to adapt to the user as the user is trying to adapt to it. And there's a lot of things that can actually come into play when we do that, which is the roadway, the topography, as well as the geography from the infrastructure perspective. But from the user, there is how much experience we have with a particular road, as well as how much familiarity. So we need to basically account for what these individual driver differences are. And there are many things that are associated with the driver, including medical and cognitive impairments. We look at things like the onset of sleep apnea or the onset of dementia, things associated with older and younger drivers. There could be things related to fatigue, distraction, inattention, and generally there is this propensity to take risks that many of us think about. Every time we get to an intersection or use a particular road, we actually weigh the risks about using certain aspects of it, whether or not we should stop, whether or not we should text while we're driving, whether or not we should proceed through any particular intersection. So therefore, when we're considering these systems and accounting for these individual differences, we also have to adjust for the fact that we're maybe driving a vehicle that has different types of devices, the traffic devices themselves, as well as the environment. So I look at it, when we look at behavior adaptation, there's two kind of aspects. There's the way a driver actually performs for a particular time and place, and that includes like how they actually steer, accelerate, decelerate, brake, park, what route choices they may use, and what type of in-vehicle activities that they do at a particular time. However, when we're looking at a pattern of behavior, we need to do that over time. We need to look at, are they going to be driving, let's say, 65 miles per hour on average in this particular roadway? Will they drive 65 miles per hour tomorrow, the next day, or the day after? And so we're looking at these variations in driving performance and trying to understand how things like those variations and their motivations for driving can have an impact on how they use these different systems. So there was a model that I worked on with a couple people here at the University of Minnesota a few years ago, Mike Manzer and Janet Creaser, where we looked at how people actually change their behavior based on system use. So the first thing is when you get a system in your car, it gets activated. And so once that happens, we assume that if it's a safety system, that your performance actually will increase based on that system. Let's put ABS, conventional cruise control, you expect that your performance will get better. Now, in the short term, you might even keep trying to improve and even get more better. But then over the long term, there's just so much that you can do. And so you're going to just sort of level off. And if anything, you may not be able to perform at some maximum performance, so it starts to maybe go down a little bit. And then if the system gets deactivated for any reason, whether or not you're using a different car, the system's not working the way it expects, so that you turn it off, your performance might actually go down. But the goal is the safety system is doing what we expect it to do. We actually hope to have some sort of a positive transfer. In other words, what we learned from using that system will kind of remain with us such that our performance will hopefully be better than what it was before, even when that system is no longer there. However, the more likely case is that when that system is gone, I'm just going to go back to what my performance was and just drive the way I normally do. Now, of course, alternatively, the flip side is I got so used to that system that I was expecting it to do a whole bunch of stuff for me, so that when that system is no longer there, I'm going to become maybe less aware, less knowledgeable about what to do in a particular situation. And in that case, I might actually have a negative transfer. So these are the three different possible scenarios, and there's different continuums of that in terms of how people adapt to different technologies. Now, when we look at that, there are different ways that we can actually quantify that behavior. So if we're trying to model how people behave in different situations, we can start off by looking at their immediate response to a particular system. So by doing that, we're looking at what their actual risks are as they're using that system in a particular environment, given whatever the risks are at that particular moment in time. So how would you do that? So we can actually use things like naturalistic data. We can look at the crashes that have actually occurred in the past and try to take a look at what's going on. And maybe the crashes only tell us one part, but maybe we can look at those crashes in addition to moving violations. In other words, we can look at just observationally what has been going on with that particular driver. So if we want to look at using naturalistic data, in other words, setting up a video system in a person's car or just observing them through whatever means, we can actually do that different ways, but the value is that we can capture what these driver-initiated activities are. Why is it that they might actually use a system in one way for one particular scenario, but may not so in another? So it can provide insights into this driver behavior for different types of environments and help us actually identify what the context is associated with those safety critical events. Now, of course, the challenge is it's hard to always see what these interactions are with new systems, because oftentimes not actually all to the same degree. But we can maybe have more focused kind of studies looking at these things. So I've actually spent a lot of time looking at something called adaptive cruise control. I asked this question yesterday. When we get vehicles, we have a ton of different technologies in the car, but we're not going to be using every single one and not actually all to the same degree. But we can maybe have more focused kind of studies looking at these things. So I've actually spent a lot of time looking at something called adaptive cruise control. I asked this question yesterday, but I'll ask it again today. How many of you know what adaptive cruise control is? Some of you? Okay, good. So for those of you who do not know what adaptive cruise control is, it's basically a system that you can set it to something like 70 miles per hour. And if a car goes in front of you, you can actually set what the gap setting is, such that if the gap setting of the car, your car and the car in front gets too close, your car will actually slow down. And when this car is away or moved forward, it will speed back up to the speed that you actually set it. So it works like conventional cruise control, but it adapts to the situation around you. And this system has actually been around since 2001. So a lot of people actually have this system in their car and they may not actually be aware of it. So there was a field operational test that was done at the University of Michigan Transportation Research Institute on intelligent cruise control, which was a precursor to adaptive cruise control. It was actually designed to work exactly the same way. This was done in 2003 to 2004. What was really nice about the study is that they had 60 some odd vehicles. All of these people never used adaptive cruise control before, so we can actually see what their novice behavior is. So we were able to actually look at these drivers in real-world situations using adaptive cruise control, and we examined their basically trajectory as they closed in on a lead vehicle. So you can see that there are different ways that we can collect information. So these are two different drivers. One of them is you can see their trajectory. They were in the low-risk situation for some time. Then they started getting too close to conflicts and almost hit the near crash before they kind of fixed themselves. Or the system basically gave information to say, slow down. In this situation here, the trajectory was such that they were always in a conflict situation. They drove really close to the car in front, and then they were actually in a near crash situation before it kind of subsided. So the way adaptive cruise control works is that it will actually slow you down in the situation, but you can also intervene. In other words, if you don't trust that the system is going to slow down for you, you can actually press on the brake and slow down yourself. So we actually looked at these different responses in a different way, which is we said, well, if here's an example of a conflict event, and here's one of a near crash. This is you, the test vehicle in green, and then you can kind of see what the trajectory is of you in comparison to the lead vehicle. So regardless of whether you're in a conflict or a near crash situation, you would expect that the adaptive cruise control would give you a signal at the same time, which is what it does. When it's approximately about the same distance away between the test vehicle and the lead vehicle, you would see that the ACC gave a warning. However, what you might see a little bit differently is what happens next, which is that the driver may actually respond a little bit differently. In a conflict event, they actually respond much quicker. But in a near crash event, you can see that this particular vehicle, the lead vehicle, starts slowing down a lot more, so they get closer and closer to the test vehicle, but the driver actually took longer to respond. So in the near crash events, which are actually much more safety critical, it may take longer for the driver to respond, and if the ACC is not going to intervene appropriately, then you could actually have a very serious situation. As a matter of fact, when we looked at the response time to these conflict events for these different scenarios where there's a near crash where the ACC basically responds, and a near crash where the ACC responds and the driver intervenes, etc., we actually see these different types of patterns. Now, what this graph says is that if you're on this side, which is where a long tail distribution is, this is where the controller actually responded earlier than the occurrence of the conflict. And the controller could either be the ACC or the driver in this situation. Now, on this side, basically, the controller actually responded later. So if they responded later and they respond too late, it could actually be a bad situation. So you can see from the black distributions, which are the near crash events, you can see a big difference between the ACC plus the driver and the ACC only. So the ACC actually takes longer to respond when a near crash event. Now, in the blue line, which is the conflict events, when the ACC alone intervenes and the ACC and driver, it's about the same. You can see because the distributions are on top of each other. So these are situations that we wanted to take a look at in greater detail. So we basically used this data. There were 66 participants, equal numbers of males and females, and 3 age groups, younger, middle-aged, and older. And we set up a logit model with repeated measures because there's multiple observations per participant. And there was over 4,000, there was almost 4,000 closing events, with 459 of them where the driver actually intervened. In other words, the driver took over for whatever reason. So we set up a logit model to take a look at what is the likelihood that the driver is going to intervene in this situation, given the fact that there is an adaptive cruise control system. So we actually, after this model, so the way to interpret this graph is that they're less likely to intervene if they're on this side, on the right side of the one, and then they're more likely to intervene on this side. So what this graph says is that they're in the highway, they're actually less likely to intervene. And that makes sense because if they're on the highway, they feel more comfortable with the car being in front, and the ACC should be able to take over for most situations. Whereas if they're younger, they're also less likely. If they're older or middle-aged, they're more likely to intervene. In other words, if you're an older individual, older or middle-aged compared to a younger driver, you're more likely to press on the brake, and you're less likely to let ACC kind of take over. And then what these green dots are, this is how you actually set the gap setting. So on this particular vehicle, you can set it as very, very close, somewhere in the middle, or a little bit further away. So what this is saying is that you set it on the very long setting, that you're less likely to intervene, that you feel more comfortable letting ACC intervene because you've allowed enough room for that to happen. So it's interesting because you get this kind of information using naturalistic data, which is, what are the situations where the driver is most likely to intervene and what's going on. But you can't really see, exactly what the specific situations are or why these particular drivers are doing things that they're doing. So the challenges of naturalistic data is that we can parse out all these differences, but there's lots of variation. Every single one of those situations has some other scenario with different people, different vehicles, different road configurations, different weather conditions. And some of those measurements may actually not be as good. Now this naturalistic data collection system was in 2003 to 2004. So some of the measurements may not be good due to adverse weather conditions, the lighting, the glare. And then also, even though we're looking at like these one factor in a naturalistic study could actually be a multitude of other factors. So the variation that you see among some variable of interest may actually not be consistently observed. And then of course, the sample sizes are definitely not going to be the same. So just to give you an example, let's say I'm interested in the impact of driver distraction on crash risk. Well, driver distraction, if I wanted a code that said driver distraction, yes or no, that's actually dependent on many different things. What is the type of distraction? The type of mobile device, if the distraction happens to be a mobile device. Where is the location of the device while I'm driving? Because that might actually have an impact, as well as how I'm interacting with the device and what are the circumstances associated with it. So why this is important is because when you look at studies that come from naturalistic data and simulator studies, you might actually see different results. And so one of the reasons why is because how it is that you're looking at this data. So for example, let's say I'm looking at cell phone dialing, okay? And if I do a naturalistic data study, I might actually see that the distribution is skewed more toward one side, which might suggest that you have quicker response time when you're using a cell phone. Really? That's amazing. But yet, at the same time, we do see some protective effects associated with cell phone use. But however, what if it is the case that the cell phone dialing is associated with 3 different types of dialing? Let's say one is touch screen dialing, handheld voice dialing, and Bluetooth dialing. And because there's a lot of laws on the road about the fact that you're not supposed to use handheld, you wouldn't really see that many observations of one compared to the other. So with Bluetooth dialing, you may see that which has 900 observations may actually skew the distribution more toward one side compared to the other. And if you were to look at these in a little bit more detail, let's say we look at the touch screen dialing and Bluetooth dialing, where somebody might still have a flip phone where they're just pressing buttons, or they're using Bluetooth, we may actually see that for the touchscreen dialing, that there were 75 participants in this category, and there was only like 1 to 3 observation. In other words, only half of the sample was unique. However, but in the Bluetooth, it may not be that much more. It was like 90 participants, and because they used Bluetooth quite often, there might be 5 to 15 observations associated with that. So only 1/10 of the sample is actually unique. So these are things that has to be taken into account when you're analyzing this type of data, and that's really important. So when we think about what repeated measures are, which is what we do when we're looking at some of these studies, going back to the logit model with the repeated measures, we have to take into account how these observations and how the differences are actually correlated. And there's going to be different types of variations associated with changes in time, and we have to consider what that covariance matrix is. I'm not expecting you to memorize this, and actually these are not just the only two types of covariance matrix. But my point is to show you is that there are differences in how the relationship between different points in time are linked together. And that has to be somehow accounted for when you're doing your analysis. So the other thing that's important to recognize is that when you're looking at these different variations and these different covariance structures, is that different types of repeated measures. Participants could be observed over different types of condition, like weather, different rows, different days, and you want to be able to capture that. And if we're looking at days, there could be different types of measurements in time that are more equally spaced. So you want to take into account maybe every second, every hour, every week, every month, and you want to be able to account for that. And that is very different from just looking at a before and after study. So depending on what it is that you're trying to answer and what your research question is, you might want to actually take that into consideration. So I give this very, very simple example of this relationship between these dots of A and B. So to everybody who's looking at this, you would say that A is positively related to B, right? Or is it? So what if I told you that this is actually 3 different participants, and the 3 different participants actually looks like this? So what you thought was A being positively related to B might have actually be completely the opposite. So if you don't take into account that within subject variation associated with participants that you're looking at in terms of data, your outcomes may actually be different from what it should be. So going back to this graph where we can try to capture what the actual risks are, but at the same time, there are other motivations that can be driving the user, which is there's the long-term exposures. I may have used this route for many, many times, and so I have a perception of what the risks are associated with that intersection. I have a perception about how many pedestrians or bicyclists I see, and so I may be willing to take more risk, or I may also know exactly what the timing is of that traffic signal. So I will be willing to take risk for a different reason. So there are different types of motivations, attitudes, and biases and experiences that all have to be accounted for when we're thinking about looking at these different systems. So for example, going back to adaptive cruise control, there are actually many differences across these systems between makes and models, between the number of gap settings, the types of gap settings, how long the gap settings are, the different types of displays I see with adaptive cruise control, and then what types of configurations they are, and what the capabilities are. So many of the earlier adaptive cruise controls actually had a lot of problems being used in stop-and-go traffic. If there was a vehicle stopped in front because it was based on an algorithm that was based on 2 moving vehicles, it really could not detect things if the road curvature was too large because it's based on a radar in front that has a certain field of view. And if you're on a curvy road that actually surpasses that, you're not going to be able to use it appropriately. So again, this system has been around since 2001. And what we did is we did a survey in Washington State where we sent it out to people who potentially had adaptive cruise control as part of the vehicle that they purchased. And we asked them this question. We said, can ACC actually help you in stop-and-go traffic on curvy roads and for stopped vehicles? The correct answer is no. You should not be able to help you, but yet you can see how many people said yes or don't know. So some of you may be thinking, well, guys in the Pacific Northwest, what do you know? Well, we actually did the same study in the Midwest, in Iowa. And in Iowa, look at how low these people said no. So in general, overall, over 50% of people who own adaptive cruise control are not aware of the limitations of the systems that they are using in their car. That's a problem. So if you're not familiar with what the system is and what the limitations are, and you expect it to slow down when it's not going to slow down, you might actually be in a potentially more safety situation than you normally would. So one of the things to kind of bring this all back together is if we have information from the naturalistic environment, just observing what's going on, we understand what people's motivations are, what their understanding is of the systems and the limitations and biases, then maybe we can understand what their response are and test it out in a more controlled environment. And that's where a driving simulator actually could be very, very useful, because you can use a driving simulator to repeat and look at things over and over again to see what kind of outcomes there could be in certain situations. So the observational studies, the naturalistic data, can actually show you what particular situations you want to be able to simulate. You can understand what the limitations are and then be able to test for it in some ways. So that's what we actually did. So I actually use driving simulators for many things. That's me using my cell phone in a simulator, not on the real world. But the nice thing about simulators is that you can actually examine potential road and vehicle improvements. So there's more like before you actually deploy it. And it can help guide the design of advanced driver support systems even before they're on the road, because that's the other thing about driving simulators that are very valuable. You can use it to look at systems that are not actually deployed yet. You can look at different types of road configurations before your state agency actually puts it on the road and spends a lot of money on it. And you can also use it to identify what the magnitude is of the effect of that particular performance. So it's nice because you can have repeatable outcomes. And if you design your study correctly, you can get very, very close to equal sample sizes for each of the conditions that you're interested in testing. So we actually did that with adaptive cruise control. We looked at different patterns of adaptive cruise control, and we brought people in that actually use the system. So not just that they're novice drivers, but they've been using the system for at least 1 year for X amount of miles, and we wanted to see how well that they would be using it. So if you remember what I said earlier, every single adaptive cruise control system is a little bit different. So we actually just focused on one group of users. And at the time that we did the study, when we did the surveys to figure out what is the most likely type of car, most people owned either a Toyota or a Lexus that had adaptive cruise control. Toyota and Lexus is the same parent company. Their system is almost identical, if not identical. So we basically used the University of Iowa driving simulator because it was motion-based, because we wanted to look at different types of scenarios. And we set it up so that we actually had the steering wheel set up with the exact same types of controls. They can go ahead and set the gap setting the way they want, as well as what the posted speed, as well as what the speed is. And they had a display so that they can actually see what types of settings that they had. So this was exactly the same system that Toyota had in their car at that time. So we collected 24 drivers. They were experienced Toyota and Lexus ACC owners. Their mean age was 56. People always ask me, well, how come you didn't look at younger people? So one of the criteria for participating in the study was that they had to have owned these Toyota or Lexus vehicles. And the majority of people that owned these, they were higher end vehicles, were people that were older. So not a lot of students owned these types of vehicles at that time. So we collected information. We had them drive through several different routes, and we just observed how many times they engaged their ACC, disengaged their ACC, the number of times ACC issued a warning, and the percent of time that they set it at different settings. And so we did a cluster analysis to look at this group of drivers, and what we found was that when we looked at this data, they can actually be parsed into 3 different cluster groups. One group basically, let me just put this here. One group here appeared to be more conservative. They actually disengaged their ACC a lot more than the other 2 groups, and they also set up their speed at typically lower than what the posted speed is. Whereas the group on the bottom, actually, we consider them to be more risky. They disengaged the ACC less. In other words, they let ACC go ahead and turn on and slow them down, and they were approximately above the posted speed limits by just a little bit. So when we looked at these categories, we basically put them into cluster groups. I just named them the conservative group, a moderately risky group, as well as a risky group. So why this is interesting is here it is, there's a group of drivers, pretty homogeneous in terms of like their age range, in the middle age range, but yet they use ACC very, very differently, and all of them have the same type of ACC. So we then asked them some questions about what their trust was in the adaptive cruise control. And we did this on a 5-point scale. We had 12 different questions. I'm just going to show a couple here. And then we also asked some questions on driving styles. So the trust questions were, we just asked them, did you do you have some overall trust in your adaptive cruise control? Do you trust that the adaptive cruise control is displaying the information correctly? Do you trust that the adaptive cruise control is in cooperation with you, and several others? For the driving style questions, we wanted to get a sense of who these drivers were. Do they tend to drive fast? Do they tend to plan trips in advance? Do they tend to ignore distractions? So when we went back to these three groups of people, the conservative drivers, the moderately risky, and the risky, we see that the conservative drivers had about an appropriate level of trust. They had high level of trust, but it was appropriate for what they were using for the ACC. And they actually noted that they had very cautious driving style, which matched actually like how they drove, like, you know, putting their posted speed at a little bit lower than what it is. Moderately risky drivers had the lowest level of trust in the ACC, and they were actually more confident in their own driving skills, and they tend to drive faster. The risky drivers here, they said ACC is great for everything, and they basically tend to overtrust ACC, and they were actually not aware of the system limitations. So the questions that we asked, like the broader community about whether or not your ACC system is going to work in stop-and-go traffic, you know, on curvy roads, they said, yes, 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 it's going to work for everything. And these people also tend to be the most easily distracted. So here it is, this group of driver, which was actually a small group. But these individuals tend to overtrust their ACC. They tend to be very, very easily distracted. And they're the ones that are using the system perhaps not in the way that would be designed for by the manufacturer. So it's interesting because you know, we're looking at these types of systems. And so many of these systems that we're putting in the car manufacturers are saying that they're convenience systems, but many people are viewing them, because one of the questions that we ask is, do you view this as a safety system? And many people feel that they could be safer when they're using these systems, even though they're not marketed as such. So is that true for many other things that we do in the car? So we actually did another study just looking at in-vehicle information systems, just doing texting or reading in the car. And we wanted to see whether or not people just adapted to their in-vehicle system in a way over time. Some of it might be more positive, whereas other times it may be more negative. So you could have positive and negative adaptation. So positive adaptation could be that the driver maybe decreases their eyes off the road and spends more time looking at the road. But the opposite way is that negative adaptation is they could spend more time looking on the system because they think that they can maintain the road condition better. So we actually did this study with 28 drivers and had them engaged in different things from text entry to text reading tasks of varying lengths. So when we looked at the study, so we actually varied the number of characters. So we had like things like you could enter text like blue, you know, B-L-U-E, and you would have to type B-L-U-E. Or we could have some word much bigger like elephant, and they would have to type that in too. So we had these types of text entry tasks with like a small number, a medium number, and a large number of characters that they had to type in. And then we also had a reading task where they just had to read in, like, let's say like a variable message sign, you know, snowplow ahead, you know, maybe 30 characters. It could be snowplow ahead, move over to the right-hand lane, you know, so 70 characters. Snowplow ahead, move over to the right-hand lane because, you know, you have to do blah, blah, blah. So, you know, we basically looked at like increases in the different characters. So you can see by the eyes off road time, this is their maximum eyes off road time during these different tasks. And you can see that it does increase with more characters. But what's interesting is, and in many of the studies that we actually look at, typically if your eyes are off the road for more than 2 seconds, that you're more likely to be involved in a crash. So if you look at this graph at the 2-second mark, even entering 4 characters could actually be problematic, because you can see that you can actually go up to like 2.5 seconds. But it's interesting because it's not like it's not a straight line, you know, because it's not quite linear. So it's just something to kind of think about. And when we're looking at this data, we can see that, so what this is showing here is going back to like looking at repeated measures, is that we also want to make sure that we take into account that everybody does things a little bit differently. Each line actually represents a different individual. So you can see for the text entry, there's a greater spread in the data for entering data compared to reading data. And so this is very important. And then you can also see, like, if this is one individual, so if they tend to like look off the road quite often, they will probably look off the road much longer than somebody who's down here. So we also looked at this data in the context of, you know, so we looked at it for just one day, and then we brought them back in for another day and another day to see if that would have an impact. So when we looked at these eyes off row time, you can see that with the text entry task, so from day 1 to day 3, they actually increased the amount of time that they looked at the in-vehicle task. With the reading task, it was about the same. I mean, it increased slightly, but not as much as the text entry tasks. So we had these people come back, and that's what we see. However, what's very interesting is even though they had their more eyes off row time, and then again, this is like the 2-second rule, so you'll see where that is. You can see when we looked at their standard deviation of lane position, like how much variation there is. In the when it was longer, the text entry was longer, you can see that they have much greater variation. But in general, it's not really increasing the way that the eyes off row time is. So what's really interesting about this is people, they got used to the task, and so they tend to look at it more often, but yet they seem to still be able to maintain their row position. Why this is interesting, and you can say scary, is that people start getting more and more confident that they're doing things the right way, but if there's a situation where something just comes darting out, you may not actually be able to respond as well because you're not looking at the road as much as you were in the beginning of using this device. So something to kind of think about when you're driving and you think you're very confident in texting your loved one on their phone after several times. Now, of course, these last 2 studies that I just showed were in a simulator, and in one of the challenges that people have always mentioned is that this is not the real world. So whenever I write papers on this, I have to have a limitation section that actually identifies what those limitations are. But that being said, if you want to be able to see a scenario over and over again and understand like what would happen and what the magnitude is of the change, a simulator is great for doing something like that. Now, of course, you can't really control for everything in a simulator. There are some things that you need to vary. And also, you also want to be able to see some sort of levels of varying traffic. The other thing that has been a concern in a simulator study is the likelihood of simulator sickness. We had this older individual who was a fighter pilot in a previous life, and he hurled big time. So these are things that you don't really want to see in a simulator, but at the same time, you want to try to get a representative sample, but you also have to recognize that there are biases associated with those who actually can participate in the driving simulator. And the other thing is, if I do have repeated conditions within a participant, there are some learning effects associated with it, and that has to also be taken into account. But of course, there is value for both the naturalistic and the simulator studies, which is in the naturalistic, you can observe the varying traffics and other types of road users, but in the simulator, you can control for that, which is, so both of them are of value to be able to look at. And also, both of them can be complemented with other types of data. So you can use video data, eye tracking data to take a look at other things. We've used physiological measures like heart rate monitors, EEG, to be able to look at different things. And both encompass multiple observations per subject, per vehicle, per day. So just doing a simple t-test or pairwise comparison is really very difficult because you want to be able to account for all these individual variations that I've sort of brought up. So, I talked about just driving simulator and naturalistic studies, but there's actually a whole bunch of variations that you can do when you're looking at modeling the effects of adaptive behaviors. You just have to recognize that depending on which way you go, you could get closer and closer to the real world, but you would have less experimental control. And so my point is that there is value in doing all of these different studies, and I've actually have studies in almost every single one. And the reason why is because there are some times where you just want to be able to see whether or not there's a differences in something very subtle. And other times, you just want to be able to understand what's going on in the real world. And so somewhere in between will give you the complete answer. So you can't really just rely on one particular data collection tool to get insights on modeling, behavior adaptation. You really do need kind of a gamut of different techniques and understand how to kind of bring them all together. So when I think about adaptation to technology, another area that we're kind of looking into is where we've spent a lot of time trying to understand how people use different technologies that are supposedly mounted in the car. But of course, all of us know that we can actually bring in technology. So when we did a contextual interview looking at how people use voice interactions, we found out that even people who have in-vehicle systems in their car, like the Ford Sync or whatever, they will still supplement with using an in-vehicle device. So oftentimes people are not just using one device, they're using a multitude of devices in the car. And so if there is a combination of different things, how do people actually switch back and forth from one system to the next while they're driving? And I'm not going to mention any names, but somebody actually has multiple apps while they're driving. And so how would you actually capture that type of information? And more people are doing this, by the way. So this is very, very interesting. And if you want to be able to collect data and look at that, I think that would be very, very useful. I also talked about adaptive cruise control. So the system that I'm looking at is embedded inside the car. However, those of us who are students don't really need to actually have a high-end car. It's actually in mid-level cars as well. You can buy a $4.99 app that actually can get you adaptive cruise control. This is the ION Road Augmented Driving. It's $4.99, and it can give you information about how safe, careful, or warning you are to the car in front. And not only that, but it can also give you other information with regards to like calling. It's like an OnStar program, and it can tell you headway, collision warning information. So there's been thousands, tens of thousands of users on this. And if you read through them, most of the people are like, I love it, I love it, I love it. And then you read about this one father who goes, yeah, I bought this for my daughter hoping that it will help her maintain her road position, but I actually took it away from her because she kept looking at the device because it's on your iPhone, it has to be mounted on the car, and not looking actually at the road in front. And so he got a little bit nervous. But it's been available now for like 3 to 4, maybe I think even 5 years. The other thing, though, when we're capturing behavior adaptation, is that there are different ways that we can actually do this. So it's not even just the data collection tools, but what devices that we're using. So if people are using both, what they have in the car and the mobile devices, and sometimes a combination, it would be very useful if we can collect data from all of these different sources. So we can maybe capture the spatial, the temporal, and the individual differences from all of these different sources, whether it's from the mobile device, the OEM installed, or even a combination. And for the combination, it would actually be even more interesting to see how often they change systems while they're driving. How often do they go from the OEM system to the mobile device and back? And one way that you can do this is, if you know what Waze is, this is basically a crowdsourcing system that in 2013 Forbes reported has 50 million users. So with 50 million users, you have at least 50 million data points. And so you can actually capture all these different changes in behavior given different traffic conditions, and you can solicit that from a broader driving community. Now, that being said, there is a bias associated with this as well, as there is with many types of data collection in terms of who's actually using Waze. I mean, yes, there's 50 million people, but there's 150 million that are not using it. So what are some of the differences, and then how do we actually capture those trends? So understanding, who the population is, as well as who the non-users are, and being able to compare that is actually really important. So my parting words are that, there's a lot of increases in technology, and so, there's all these different safety issues that will continually arise. But hopefully, I gave you a flavor of all these different types of data sources that you can actually get information from. And they do not, in my mind, compete at all against each other. They're very, very complementary. And they answer many different types of research questions. So we just have to identify what those differences are and how we actually use those tools together. But in general, to me, data-driven outcomes are so important. And they're basically used, depending on the tool, to identify either the causality or the association. So if you understand what those differences are, then you can use it to validate what your framework is for your driver model. And again, understanding what this triangulation of all these data sources is very, very important. And if you understand that, you can actually get a very good picture of how people behave on the road. And with that, I just want to thank you for listening to my talk. All of the work here was basically based on work that my PhD students helped me with. And funding was from NSF and NHTSA, as well as the National Academies. Thank you very much. And I can open it up for questions.
Just want to remind everybody that you need to use the microphone if you have a question, and we certainly welcome questions from the audience here. Anyone care to start?
My question is primarily based on some of the limitations that you talked about.
Yeah.
So you touched on a few, including curvy roads, stop-and-go traffic, or a stopped vehicle. One that I'm wondering how it aligns with that is a vehicle. Say you set your separation distance fairly short, not real conservatively, and a vehicle in front of you slams on the brakes. What is the ability of adaptive cruise control to slam on the brakes? Is there a limitation on how much it can decelerate you, or
The
how does
answer
that
is
work?
yes, there is a limitation on how much it can. We have a paper actually that we looked at this, and the adaptive cruise control can stop you if it has time to stop. So if you just slam on the brake because you're so close, there is a high likelihood that it will not actually stop in time. So that's the reason. So going back to when the driver should intervene and what the limitations are associated with the system, you have to really understand what the limitations are of your system, and it may not actually stop you in that situation.
My question might be very related to what he just asked.
Yeah.
So it was interesting, the graph that I showed that is a braking response time for conflicts and near crashes, and the braking response time for the during the conflicts for the ACCs are much longer than the near
Oh,
crashes.
so is it the green and the red chart?
Yeah, I guess there are multiple.
Yeah, so what this, and maybe maybe I have to have my student redraw this to make it clearer, but here, I'll show you this one, right?
No.
No? This one?
There are multiple, like you.
Yeah, so I'm going to go through this. So basically here, let me just, so there's the test vehicle, that's the vehicle that you're in, and then there's the lead vehicle. So the y-axis is the speed that they're traveling at. So the lead vehicle is going slower than the test vehicle. So in this case, basically, the lead vehicle is slowing down dramatically, but your vehicle is not. You see that? So this vehicle keeps slowing down, it's going to get closer and closer to you. So at some point, what happens is, at the exact same point, the ACC is going to give you a warning, right? And so kind of going back to this gentleman's question, if it slows down dramatically, the ACC may actually not, so it gets engaged, and then it will start to slow down. And in this situation, the ones that I'm just showing, is when the driver actually intervenes. Because in this case, the driver responded because the ACC has not responded yet, in this case, because it's going down so quickly.
So is that can SEC can adapt to such kind of instant changes in the speed profiles, like?
I'm sorry, could you say that one more time?
Is that possible? Like the SEC can adapt to such instant decrease in the
So
speeds?
that is such a good question. So in the systems that we tested, as of 2010, no. But many newer systems are actually able to do certain things. So they're becoming smarter. So for example, like in the stop-and-go traffic, I think it's BMW or it was Mercedes. One of them actually designed a system where it can actually detect the lead vehicle in lower traffic. So most of these systems, you're not supposed to be using it when it's below 25 miles per hour. But in some of the newer systems, they're actually designing it so that it's learning how to adapt. But in the older systems, no.
Anyone else?
So I saw the data that you were using where they were reading versus doing text entry. That
Yeah.
was like 2014 data, so
Yes.
fairly recent.
Yes.
I'm wondering, so reading is one of the most over practiced tasks that we have.
Yes.
But we have a whole generation of people that are like the only way that they interact with the world is through a smartphone, basically. So do you think that number is going to continue to get smaller, that we're going to get better and better at not having to spend so much time visually devoting, or you think we're kind of as best as we're ever going to get in that performance?
So I guess I feel that humans have limitations, and we can just get so much better, but we can just do so much. We can just read so much, and I don't really have a good answer for that, but I think we are reaching our peak. I really do. And the other thing that really not bothers me, but worries me, is that in the car, there's so many other things to look at. In my driving simulator experiment, we only have them focusing on this reading task, right? But in the real world, you're not just focusing on this reading task, you're looking at the reading task and maybe what's going on here, 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 and here. And by the way, our driving scene was very simple as well. So if there's any other furniture, or other things, or billboards, it could be very problematic in my mind. Yeah.
You know, clearly newer cars have active braking going on. The older model cars like 2010 were basically using downshifting on the transmission to slow down. Do you see that active braking? I think Volvo was amongst the first to have active braking, and other vehicles have introduced them as well. Do you think that will improve the kind of situation that you've talked about over here?
Maybe. So what a lot of these car manufacturers are doing is trying to figure out how to integrate a lot of their systems together better. So it's interesting because a lot of car manufacturers want to be the first to basically deploy certain things. And it may not be perfect when they're deploying it, but it's, in their mind, near perfect. So a lot of things like going back to the earlier versions of adaptive cruise control did not work maybe as well as what they're doing now. But to answer your question, I think they're trying to do it. So is that a diplomatic answer? They're working on it.
Any questions from the internet? None? Okay.
So I had a question regarding the app that you showed, Ion Road.
Yeah.
What kind of technology is it using, and how is it different from whatever we are targeting to use in the future? Because from what I see, it's probably using some image processing kind of thing.
Yeah, I'm actually not sure what it's using, quite frankly. I know it is GPS based.
Okay.
Yeah, I'm not really sure. I just know that it has been around for some time because I looked it up because I was trying to see if there was such a thing as an app for adaptive cruise control. And the first time I presented this, I was looking up all the reviews and I was trying to download this, and I thought I really should not download it because I might actually use it. So so I'm actually not sure how they're actually designing technology. Now, this being said, this is not the only system that's actually available out there. There's actually many different systems that are driving related, and you can, and even Max has an app that that's based on like what's going on in the road.
Thank you.
So Gary had a question.
Yeah, Linda. So in the first part of the talk,
Yeah.
I guess the question that was posed was, does, for instance, adaptive cruise control help or hurt?
Right.
And then you gave us some results from naturalistic driving, and you gave us some simulator results. So let's
Yeah.
come back to the question.
Yeah.
Okay, does it help or hurt, or is it too soon to tell?
Okay, it depends. So it depends on what the situation is. So in freeway driving, it's actually, can be very useful, but you still have to be aware. So the issue is that because we're not at fully autonomous vehicles, we're at semi-autonomous, you as the driver still are the controller. You're still playing a major role, so you still have to be vigilant. So as long as you're vigilant and you recognize what the limitations are of your system, it could be helpful for various situations. But it depends.
Any other questions here? Well, please join me in thanking Professor
you very
Boyle
much.
for a very interesting talk. I would just like to remind you about next week's seminar, same time, same place. Professor Dumas Gebre-Exibar will be talking about unmanned aircraft systems and traffic and infrastructure surveillance, opportunities and challenges, basically dealing with drones operating and being used for monitoring traffic and other types of situations. Imagine emergency response, et cetera, et cetera. And so he'll be here next week, 3 o'clock, same place on the internet, and same place as far as if you physically show up and join us here. Thank you very much, all.
Thank you.
extended to